Up to this point, we've spent most of the time in our last three modules looking at problems that involved electrons, and they are, in fact, the most quantum mechanical of all of the subatomic particles. However, it's useful at this point to turn our attention toward the motions of the atoms themselves, the nuclear motion. And so we'll spend a little bit of time in this lesson talking specifically about quantum mechanics of motions of the atoms within a molecule, in particular diatomics. Now, I'll remind you that in the Born-Oppenheimer approximation, we were able to take the full wave function of the molecule, and this is expressed in terms of the coordinates that describe where the electrons and the nuclei are. And the point of the Born-Oppenheimer approximation was to be able to write this in terms of two parts, one of which I'll call the electronic part, which depends upon the positions of the electrons, but is parametrically dependent upon the positions of the nuclei. Now, I'm going to write the position of the nuclei simply as one coordinate because in a diatomic molecule, the distance between the two atoms is going to be the most important for our purposes, although you should be aware that it includes theta and phi. It includes the orientation of the molecule within space. Now, this would be multiplied by a nuclear component. I'll call it nuclear, which basically describes the positions of the atoms. All right, so we'll write it something like this. As we solve this for this wave function, we're basically solving a generalized Schrödinger equation that would look something like this, where we've got our Hamiltonian for the entire molecule, including both electrons and nuclei, operating on this total wave function. And, of course, that will give the molecular energies times that wave function. So this is the Schrödinger equation. But now when we rewrite this as a product of electronic and nuclear parts, and we can also write the Hamiltonian as a sum of nuclear and electronic parts. So I could, for example, write this as a Hamiltonian of the electronic parts of the electronic kinetic energy and the Coulomb interactions, and a part that depends upon the kinetic energy of the nuclei. And that's all that's going to be in this piece of the Hamiltonian. When it's operating on this product wave function, it turns out we get what amounts to a separation of variables, just as we have in earlier cases. So this Hamiltonian will act only on this wave function, and this can only act on this wave function, but because the electronic part has a parametric dependence on the nuclear distance from one another, it turns out now that when we solve the electronic part, so if I carried through this operation, this part would not be affected by the Hamiltonian of the electronic part, so I'd have this wave function times the Hamiltonian of the electronic part times the wave function of the electronic part. Plus this kinetic nuclear energy. So maybe I'll write that as K to represent the kinetic energy of the nuclear part times the nuclear, and I should have added a electronic wave function here. This is what guarantees me the separability of this equation, or at least it assures me of that. Now, when I solve this equation, what we have, and I'll begin to put some color in here, this is the part that we've been solving all along. And what we get out of this are electronic energy levels. And those electronic energy levels are the ones we've been describing in terms of electronic orbitals and term symbols and so forth. But these electronic energy levels are in effect dependent upon this internuclear separation R. All right, so what comes out of this is a function of R. And so what then results from all of this is, in effect, a Hamiltonian that has a kinetic energy part for the nuclei and a potential energy part for the nuclei that depends only on the distance between the two atoms. And this comes from the electronic Hamiltonian, from solving the electronic part. All right, so this picture is actually a very compelling picture. What does it say now? it says that we can plug in different values of R. And each time we plug in a different value of R, in fact, it's going to affect these electronic energy levels. So what might that look like if we were to draw a picture? Okay, so let's draw a series of electronic energy levels. So a series of different R's. And let's say at 1 R over here, and let's say this is sort of our magic R where we've sort of minimized the electronic energy, we get one energy level that's here. Maybe we get another energy level that's up here for the excited state. So this would correspond in our molecule to, for example, a sigma bonding orbital, and this might correspond to a sigma antibonding orbital. Now, if we were to now change this value of R, we would get different energy levels. And so as we go to larger R, this energy level might increase. I'm not drawing this very well, but what I'm trying to indicate is that as we change this R, the energy level of the electronic parts, these electronic energy level, the lowest energy state of the electrons is going to increase slightly, with a limit up here that represents zero energy, which is the separated atoms. So if we take the two atoms apart from one another, we would eventually end up with an energy that would represent the separated atoms. As we push these two closer together, it turns out their energy levels go up very quickly. All right, similarly, for our first excited state in the electrons, the sigma star orbital, this would gradually decrease as we went to larger radii. And in fact, what we would find is that the distance, the energy distance between the bonding and the antibonding orbitals here would go to zero. And I probably should have drawn the antibonding one first because it's a positive quantity. So what we've basically mapped out here by solving the Schrödinger equation for the electrons at several different nuclear distances is a curve. And this curve is this energy that we're hypothesizing here that is a function of this internuclear distance. Well, this is in effect what becomes the potential surface for the nuclear part of the Hamiltonian. So we can think of this as being like a potential that tells us how the nuclei are going to move relative to one another. Now, this first excited state, you'll see, looks very different. It's a surface that's up here. And this is why we begin to distinguish between a bonding interaction, which is the one below, the sigma bonding interaction, and the sigma antibonding interaction. The antibonding interaction is not going to form a stable complex where the two atoms are going to want to stay close together. There's no energy that dips below this separated atoms limit at energy equals zero. So what we have are very distinct entities here, and when we start looking at this in the space that involves nuclei, these appear as potential energy surfaces. So one of the big game plans, largely in doing electronic structure calculations, is to not only define sort of what is the configuration of a molecule that's at the very bottom here, in other words, what is its equilibrium shape, but also to determine something about its potential energy surface, because it's the motions on these potential energy surfaces that ultimately lead to interesting chemical phenomena like reactions. Reactions occur on the potential surfaces that the electrons provide for the nuclei to move around on. What we're going to do in this lesson now is spend some time talking about that nuclear motion, which is going to have two predominant forms, vibration and rotation. Now, the potential energy surface doesn't say a whole lot about rotation. What we'll find out from rotation is that the shape of the molecule at its minimum is going to say a lot about the rotational energy levels, because that's what determines the moment of inertia for the molecule or its effective mass in rotation. Vibration, however, is intimately connected to this, and it's connected in the following way. If we took the bottom of this potential and we somehow fit it to a polynomial, so we did a power series expansion of this, and we just kept up to the second order terms, we would end up with a parabola basically down here. This is only up to terms of order sort of r squared. I should leave it at r. All right, so what this amounts to is a harmonic oscillator. So this becomes, in effect, our model for vibration between two atoms in a molecule. Rotation is one that we're going to focus on this lowest point here and basically treat the molecule as though it were rigid. So this is what gives us the rigid rotor model. So now you can see that even though we've been focusing on electrons during the past couple of modules, we're going to reconnect now with some of the earlier models that we were able to find exact answers for in describing how the motions of the atoms themselves within a molecule take place.